Great, it looks like the numbers are stabilizing, so I'll get started. Great to see so many of you here today, and welcome everyone to this IES webinar, Vapour Intrusion Risk Assessment in the UK. In September 2022, SoBRA published a series of 3 practitioners' guides aimed to support informed decision-making with respect to vapour intrusion risk assessment. Today, we are delighted to be joined by 4 expert speakers who are members of the former SoBRA Vapour Intrusion subgroup. I'm going to introduce each of them now, and then we'll go through all of the presentations. After that point, you will have a chance to ask questions, and you can submit these using the Q&A option at the bottom of your screen at any point during the presentation, and I will then ask these on your behalf later on. If your question is directed at a particular presenter, please do put that in the question so we know who to pose that question to. So a massive thank you to our speakers. I'm going to introduce each of you now. So we've got John Andrews, who's an associate at Environmental Protection Group Limited, specialising in vapour intrusion and ground gas risk assessment. John has over 23 years contaminated land consultancy experience after completing 9 years of organic chemistry research. We also have David Dyson, ACON's Southeast Region Remediation Team Leader, who's also a chartered geologist and SoBRA accredited risk assessor. David's primary specialism is human health and vapour intrusion risk assessment, and he has worked in contaminated land consultancy for 20 years in a range of sectors. We also have Mel Lyons, senior soil and groundwater scientist at Shell, chartered geologist, SoBRA accredited risk assessor and certified specialist in land condition. Prior to joining Shell in January 2023, Mel worked in contaminated land consultancy for 16 years and also spent 2 years in the contaminated land team at the Northern Ireland Environment Agency. Mel's specialism is hydrogeology and detailed quantitative risk assessment for controlled waters and human health, including the consideration of potential risks to health from vapour intrusion and inhalation. And finally, we have Geraint Williams, Technical Director at ALS. Geraint is Technical Director and he has 25 years experience in the contaminated land industry. He is current chair of the Association of Geotechnical and Geoenvironmental Specialists, Contaminated Land Working Group. Thank you so much. Really looking forward to hearing all of your presentations tomorrow. So we're going to dive straight into the presentations and I'll hand over to you, Mel. Thank you again.
Thanks, Ethne, and thanks to everybody online for joining myself, David, John, and Geraint for our session today. In terms of the structure of the webinar today, as Ethne said, we're going to take you through the 3 practitioners' guides that were published around about this time last year, and then we're going to follow with a Q&A session. But yeah, the chat box is active, so if you have any questions as we're going along, feel free to type those in so we don't miss any, and then we'll address them all at the end of the webinar. So in terms of the vapour intrusion subgroup, as a bit of background, the group was originally established back in 2018. It was building on the recommendations of the SoBRA 2017 summer workshop, which focused on vapour intrusion, as well as following on from the SoBRA groundwater vapour generic assessment criteria. And then the final 3 papers from our working group were published September last year, so just over a year ago. In terms of the objective of what our group set out to do, we went through various iterations, but ultimately we were trying to recognise the desire within industry and regulators for some guidance with respect to developing a robust conceptual site model with respect to vapour intrusion considerations, as well as really trying to emphasise the importance of soil gas data rather than relying on traditional soil and groundwater sampling data, and also trying to raise awareness of some of the data collection and interpretation methods available and both the pros and cons of those. So how we went about addressing these objectives, we produced a set of 3 accessible and concise practitioners' guides which aim to support informed decision making. The guides are aimed at quite a high summary level. They cover some key areas of vapour intrusion data characterization to then support subsequent vapour intrusion risk assessment. Now, we're obviously over 12 months now since when these papers were last published, and is often the case. Things have moved on in the industry in terms of guidance and publications, and there's been a number of new publications that have come out since our papers were published. But overall, you know, one of our key messages from today is that the basic principles of these guides still apply, but we'll hear about some of the more recent developments during the webinar. The other thing I just wanted to highlight is that whilst the guides don't specifically cover the actual process or mechanics of assessing vapor intrusion risks, they're really aiming to try and provide support for developing a really strong foundation for vapor intrusion characterization, starting with the development of our robust conceptual site model through to the collection of representative samples and appropriate analysis methods. And as you'll hear today, the papers focus primarily on petroleum hydrocarbon vapors and chlorinated hydrocarbon vapors. But it should obviously be noted that vapor intrusion considerations are relevant to a wide range of other volatile organic compounds. And the key really is understanding the potential source or sources that we're considering in each case. In terms of the papers, obviously that just to highlight, these were produced by members of the SoBRA subgroup. We were all volunteers. We were acting on behalf of ourselves as opposed to our employers, and the papers are freely available on the SoBRA website. If there is any feedback on the papers, feel free to submit this to SoBRA on the email address below. And just a couple of plugs for various different SoBRA resources that are available. The Early Careers Network within SoBRA is a really great active network that provides free access webinars. And in particular, we've got one coming up in November delivered by John, which will be a good follow-on from this session today, looking at the practical considerations of vapor intrusion risk assessment, as well as the library of SoBRA reports, workshop archives, and also the joint SoBRA and RSC conference that's coming up in December on current issues in contaminated land, and registration for that is open now, and the link there to the programme. So thank you again for joining us today, and with that I will pass over to David, who's going to get us started on the conceptual site model side of things. So thank you. I'm going to stop sharing.
Thanks,
and
Mel.
hand over to David. Thank you.
Just share my slides. Okay, good. Hopefully we've switched over successfully now. As Mel said, I'm going to just talk a bit about the Note 1A, which is the conceptual site model development for vapor intrusion. There we go. Right. So a very quick kind of definition of vapor intrusion from the US EPA. Vapor intrusion occurs. There is a migration of vapor-forming chemicals from any subsurface soil source into an overlying building. And if we take that into the UK guidance, the Land Contamination Risk Management EA guidance, that one of the a little bit of text from that, migration of, and I will read the grey bits, ground gases and vapours such as permanent gases, landfill gas and volatile hydrocarbons into buildings. And the reason I've obviously grayed some out is because today we're just talking really about focusing on the migration of vapours into buildings. But in reality, and as Mel just mentioned, there isn't necessarily a lot of difference in the migrate, for ground gases, permanent gases, landfill gas type as well. A lot of the processes are, the same, but for the purposes of this note and this short presentation, it's really the vapours, volatile hydrocarbons that we're talking about. Okay, so the SoBRA guide does follow the standard source pathway receptor format for defining a land contamination CSM, and I'll talk a bit about those in order really, and try and fill in some of the details and the processes involved in each part of that linkage and the uncertainties particularly within each one. So the guide provides the additional detail really in terms of the behaviour of contaminants, fate and transport processes, for those vapor intrusion linkages and the uncertainties as a key element. On to the next slide. This is the main kind of schematic in vapor intrusion diagram we have in the guide, and I'll talk about the following slides, talk in more detail about a lot of the processes shown on here. But hopefully this is can be a useful summary for people kind of considering the different the different aspects of vapor intrusion CSM and where complications, difficulties, uncertainties, key processes, key factors come into play. And I'll possibly try and come back to this slide at various times, skipping through them as we go through. So if we start with sources, the sources in the CSM, a contaminant or pollutant that is in, on, or under the land and has the potential to cause harm or pollution. That's a fairly standard definition of a contaminant source in the UK. And as Mel said, the SoBRA guide focuses on petroleum hydrocarbons and chlorinated hydrocarbons in particular. And one of the key differences, which is really important to understand early when you're developing your CSM, is between petroleum and chlorinated hydrocarbons. As NAPLs, as non-aqueous phase liquids, most chlorinated hydrocarbons sink, so they're dense non-aqueous phase liquids, but petroleum hydrocarbons will float on top of the groundwater. Biodegradation is another key difference, and it needs to be always borne in mind when you're looking at your CSM, because most chlorinated hydrocarbons degrade anaerobically, whereas petroleum hydrocarbons degrade aerobically. And there's a couple of really good publications in terms of the fate and transport and behaviour of D-NAPLs and L-NAPLs in these two publications, the handbooks. One Environment Agency, one Clare publication, which really cover in great detail the kind of the differences between the two and the processes. I thought just worth noting vinyl chloride is a clear exception to both of these rules, although it's not that common to find vinyl chloride as a free phase NAPL. It's more likely that you'll have it as a degradation product of parent compounds such as tetrachloroethene, trichloroethene. And I'll come on to the kind of the complications that poses with the biodegradation shortly. So again, just a little bit more on sources. Obviously, some of the key things: leaking underground tanks, NAPLs and contaminated water from former gas holder tanks, for example. I've got a little picture of indicative picture of a fuel station there. That's a very obvious one. Underground tanks, petrol and diesel primarily. Surface spills from above ground tanks, obviously also important. There's a kind of drawing of a picture of an oil terminal there. Again, a very one of the more common sources of large scale NAPL in the ground and vapor intrusion issues, especially if those areas are being redeveloped. Other sources may be landfills, infield ground drains and sewers, where there's accumulation of material. And then the plumes, once they're in the ground, the NAPL plumes or the dissolved phase plumes. We've also just got a little photo there of an old tannery building. So for chlorinated hydrocarbon sources, really industrial degreasing, which was what they were used for in tanneries, but also motor works, dry cleaners, that kind of degreasing thing, as well as for more chemical and industrial processes, will be some of the main common sources of chlorinated solvents in the ground of chlorinated hydrocarbons. So then moving on to the kind of some of the key things to think about in source area, the behaviour, what affects the CSM. Well, the ground conditions obviously very clearly very permeable ground means that contaminants can migrate easily and over greater distances. Low permeability ground, the opposite, limiting migration. And then the difference between heterogeneous and homogeneous ground. And you may have a more predictable source distribution in homogeneous ground, but heterogeneous ground with fractures, clay lenses, pipelines, if it's man-made heterogeneity, can really complicate the picture. And I think hopefully if I flick back in the diagram we've tried to indicate that. You can see sort of clay lenses where vapors may migrate laterally around, fractured bedrock where D-NAPLs migrate preferentially through fractures. Whereas if you've got a more homogeneous sand, for example, you might find that the contaminants migrate in a relatively more predictable or easily predictable way. Partitioning is another very important process in the source area. So the VOCs, or the contaminants, will partition into 3 phases in the unsaturated zone: absorbed to the soil, into vapor phase, and then the dissolved phase, and in 2 phases in the saturated zone. And that partitioning is controlled by various parameters: contaminant specific parameters, soil properties such as porosity and bulk density and organic matter, and then mixtures. If you have mixtures of them, then Raoult's law will control the vapor concentrations. And I think the important thing here is that there's an awful lot of uncertainty, and this is where, kind of leading on to the next 1B, 1C, about the importance of vapor sampling, as well as the more traditional, what you might call soil and groundwater sampling, because there's a big uncertainty when you take that soil and groundwater data and then start calculating estimates of vapor concentrations. And then for groundwater sources, the capillary fringe, again, it's the soil properties really, which tend to control that difference between clay and a gravel, have a very different capillary fringe effect. Okay, a couple more things in the source area. Some of these overlap into the pathways really as well, but we talk about them here. I've actually already mentioned the density, again, between petroleum hydrocarbons and chlorinateds. The light petroleum hydrocarbons, which will tend to float on the water table, not penetrate particularly deeply once they reach the saturated zone. Whereas chlorinateds will tend to, or if they're denser than the water, they can sink considerable depths through the saturated zone through fractures, particularly. Biodegradation, really important process, and again difficult to predict. Aerobic and anaerobic, petroleum hydrocarbons readily degrade aerobically, and as long as there's oxygen and some bugs there, they will really almost always degrade to more harmless products, oxygen, water. Methane will be generated, which you do have to consider. Obviously for a gas intrusion, gas risks, but often the rate of methane generation may not be as high as, if you're worrying about it from a landfill, that kind of thing. Chlorinated hydrocarbons tend to degrade much slower rate and primarily anaerobically. Again, depending on the oxygen content and the bugs in the ground, they will degrade, but they will produce, well, for example, trichloroethene, tetrachloroethene will degrade to ultimately vinyl chloride before then becoming ethene, ethane, and carbon dioxide if you've got a full degradation chain. So, and vinyl chloride being more volatile, more toxic than those parent compounds, can cause a different problem with your CSM, because it becomes a temporal issue. Through time, you may have a different profile of contaminants in your source area. Okay, so just moving on to uncertainties, really just wrapping up the source bit with the uncertainties. The location and distribution, obviously, with site investigation, can be very difficult to pinpoint the location of your source precisely. Groundwater levels, variation in the levels over time, cause the source depth to vary, and that is a very sensitive parameter, the source depth, for looking at vapor intrusion into buildings. Theoretical partitioning, as I said, partitioning is very important process, and if you're calculating it from soil or water data, there's high uncertainty in your vapor concentrations. And the limitations of soil sampling investigations. And I just want to highlight really the 2020 British standard for sampling VOCs in soil. And you can see a couple of photos there. I don't know how routinely it's used through the industry, but these photos courtesy of Geraint at ALS. We'll talk later, but you can see that actually this process with methanol preservation is one of the options from the British standard for sampling for VOCs, and there is data out there which shows that you do get some quite different laboratory results if you do it this way compared to the non-methanol preservation and just stuffing your soil in a jar and sending it off. So I think I just wanted to, if you are doing soil sampling and using that for vapor intrusion assessments, this is the way to do it. If you're not moving on to vapor sampling. Okay, pathways quickly. 3 main types of pathways that I'll talk about: conventional, which are really the kind of the typical migration of vapors through the unsaturated zone and building foundations, and maybe the ones that, in theory, it's easier to model or to assess with screening tools. Preferential pathways, much more difficult, but actually possibly one of the biggest concerns for vapor intrusion, penetrate ground. So hopefully this is where I got to before I realized I dropped out. So hopefully this is roughly consistent with where we were up to. But yeah, so conventional pathways and the types of foundations typically considered in the UK: beam and block with a subfloor void on the left there, slab straight onto ground in the middle, and then a suspended slab or suspended floor on some kind of piles or stone columns, that kind of thing, with a subfloor void as well. And they're all foundation types that can be the screening models attempt to kind of assess. But there are also a whole host of different types which can make life more complicated: earth floor basements, concrete, more engineered concrete basements with damp and waterproofing, buildings with undercroft car parks, which may have much better ventilation, good ventilation, active ventilation even, and then prefabricated modular buildings, which really may just be units kind of screwed onto a concrete slab with very limited connection between the internal space and the ground. But in reality, again, a lot of conventional pathways exist alongside preferential pathways: drainage, foundation service penetrations, and those preferential pathways can be the critical risk driving pathway, and it's very important to understand those if you can on your site. So just quickly, in terms of how we tend to look at intrusion through typical foundations, it's really cracks and openings in the concrete, construction joints, or openings at the interface between the ground slab and walls, cracks in those walls below ground level, gaps and openings in suspended block and beam floors, which for older building stock may be analogous to floorboards over a void, and then the preferential pathways: damage to membranes, gaps around service pipes and ducting, and cavity wall voids. Worth noting that lateral migration pathways can also be quite significant, and most likely when there's a confining layer over permeable horizon, so geological clay lenses or hard standing. Just some of the processes involved, and really I'm not going to go through these in great detail. What I wanted to kind of give an idea of here was that there are quite a few processes and controlling each of these elements within the pathway migration. And because of all of those different parameters and processes, the uncertainty can build up quite significantly. Even if you have estimates for these things, there's really an awful lot of uncertainty that can start to come into the pathway. And I think for the purpose of time, I won't go through each of them. Maybe pick the odd one out. Path length for diffusion certainly is a key one through the unsaturated zone. How thick is your unsaturated zone? Hydraulic conductivity, oxygen availability, really important for understanding your biodegradation, but not always easy to measure, or not often measured in site investigations. Organic carbon, understanding that and the distribution and how variable that can be through different layers in the ground. and within the building itself, mixing and dilution, background VOC concentrations, air exchange rates, all can be highly uncertain, and very much estimates, guesstimates. Just moving on to preferential pathways. Again, covered most of this. The two types really, natural and artificial, fractured bedrock and gravel lenses, or clay lenses, maybe. Some of the natural examples make it very difficult without incredibly detailed characterization of your site to understand. And artificial preferential pathways, utility features, obviously, utilities is obviously an obvious one. Even inside buildings, if you think about the lift shafts, stairwells, that kind of thing, they really complicate the mixing and dilution kind of considerations, and ground engineering, mine workings, tunnels, stone columns, that kind of thing, really can be very difficult without very detailed characterization to understand. Yeah, and so they can make the estimation of vapor intrusion risk by screening or numerical modeling highly uncertain. And you need to clearly recognize that in your CSM interpretation, and how you investigate your site. And again, that kind of feeds into the next stages of this presentation, about vapor monitoring and gas assessment. Very quick slide on direct infiltration. I think just one to be aware of, it's not so common, but if your groundwater or NAPL is directly in contact with the building fabric, then you may get permeation and saturation of that material into the, let's say, the concrete structure itself, and that really affects the indoor air concentrations. And again, screening and modeling is not something that can be done easily without much more detailed consideration. And you may be needing to look at alternative measurement approaches for your ground gases or your indoor air concentrations. Pathway uncertainty. I think realistically I've covered this talking about the other slides, but quickly to go through the significance of the advection and diffusion pathways, controlled by so many different aspects of the ground, that it's difficult to assess in a site-specific basis. Biodegradation, how much oxygen do you have in the ground? How effectively are your contaminants biodegrading? The construction of the foundations, I mentioned lots of different types, slab thickness, extent of cracks, air exchange rates in buildings, obviously climate control systems completely change the ventilation of the building and the assumptions that we often make. Presence or absence of hard standing, it really important again for preferential pathways beneath that hard standing, but also whether oxygen can actually get back into the ground for biodegradation processes, and preferential pathways. Receptors, there is not much to talk about with receptors here before I hand over. But really we normally look at residents, obviously, which can be any kind of housing, low-rise apartments, workers in commercial premises and industrial premises, visitors to those buildings, and maintenance workers, which may be a more difficult one, particularly for maintenance workers in subsurface confined spaces, something that really you need to consider quite separately, in quite a separate manner, often if you're looking at large manhole chambers that people might be having to go into. I think just to pick out the key aspects of receptors that really affect vapor intrusion assessment: the breathing rate relative to body weight, and the exposure duration and exposure frequency. So if we were to pick out a kind of a non-standard scenario like a school, it's really important to think about the duration and frequency that a child might be in a school, because it's not really like any of the other scenarios, but it can have a really huge effect on the vapor intrusion risk assessment. So those aspects are really important to consider with your conceptual model. Again, uncertainty. Just 3 points. Who are the receptors? Again, if I take the point of the school, it can have a really major effect on your vapor intrusion assessment. The air exchange rates and ventilation, so how is that building used, can really affect those. And again, they have a large effect on the assessment. And the last one is really the same as I've just mentioned, the breathing rate and exposure duration and frequency. They all have really big effects on the risk profile or the risk assessment outcome. So in summary, the CSM, it is difficult to characterize reliably because there are so many uncertainties and different parameters and aspects of each part of the linkages. Consider vapor monitoring to help the source, and obviously, and John and Geraint are going to really talk through more about that and understand your biodegradation. The screening distance assessment isn't something we talk about a lot here, but because petroleum hydrocarbons degrade pretty reliably and quickly in the subsurface in most circumstances, it is an option that you can consider looking at for your assessment. And migration along preferential pathways, really, again, just to hammer that home, it's a key part of it. So key message, I suppose, even if you consider all of the main elements of your CSM, you've got a pretty detailed site characterization, there's still likely to be high uncertainty. And alternative vapor and air monitoring approaches and techniques may help to reduce these uncertainties and provide a more reliable assessment. And with that, I will be passing on to John to talk about, to elaborate on those kind of things.
Okay, well, thanks, David. So as mentioned, I'll be talking about the benefits of soil vapor sampling to better assess vapor intrusion risks, and naturally there is a bit of overlap with David's presentation, but I think it's kind of worth kind of reiterating some of those. So I'll start with some key. I've got a few things on my screen. I just need to. Some key conclusions, and if we go through these and just bear these in mind as we go along. So as David talked about a lot, we really need to develop, scrutinize, and challenge a detailed and robust vapor intrusion CSM, and I think it's the challenge of that and challenging our own understanding of that, which is really key. And importantly, that needs to be done for current and as well as future scenarios, and they can be quite different, and they can be quite a few changes between the current situation and potential future situations as well, particularly on development sites. And as mentioned previously, there are significant differences in the fate, transport, and risk of petroleum hydrocarbons and chlorinated hydrocarbons due to differences in physical properties and biodegradation, and we'll go through that in a little bit more detail. One of the key kind of messages here is that soil vapor sampling can significantly reduce conservatism in vapor intrusion risk assessment compared with just looking at soil and groundwater. But I think one of the key things really, it's not just about reducing conservatism, it's really to soil vapor sampling better informs your conceptual site model and provides part of a multiple line of evidence approach to looking at vapor intrusion. And finally here, it's certainly not recommended to conclude that there is significant vapor intrusion risk assessment, either in existing scenarios or future scenarios based solely on groundwater or soil VOC analysis and assessment. This is unless a clear existing acute or short-term risk is likely. And again, it's really important to understand scenarios where there may be acute risks or short-term risks, as these may require a slightly different approach and not necessarily a stepwise approach. So again, this has been discussed, but I'll go through this really quickly. So what we're talking about are volatile or gaseous compounds or chemicals that are capable of causing significant gas or vapor intrusion risk. And we're looking at primarily in these discussions, petroleum and chlorinated hydrocarbons, primarily because of their prevalence in the subsurface, and also really to probe the key differences between these two types of compounds. Of note, there is really a divergence in approach to actually looking at these compounds. They vary so markedly that there is particularly in the USA, there's quite a divergence in approach as to how we look at these and assess these. Again, there are other things that we might want to consider, SVOC, so compounds that are not necessarily classically volatile can certainly cause indoor air, either inhalation risks or odor risks, particularly where you have these kind of, say, for example, fuel oils in direct contact with building fabric. They can cause high levels of indoor air concentrations, not through classic vapor intrusion kind of mechanisms. Again, ground gas we've talked about, radon, inorganics, including hydrogen sulfide, and also metals, including mercury. So the key thing here really is they're all basically just chemicals with different source profiles, physical characteristics, and toxicity. And it's important to understand the sort of key kind of similarities and differences. So radon has a predictable half-life, and petroleum hydrocarbons biodegrade. And differences being that methane causes risk at percentage concentrations, whereas petroleum hydrocarbons and chlorinated hydrocarbons cause risks at parts per billion concentrations. So big differences there. And lastly here, do think about flux. So that's the concentration flow over time, and not just concentration. I think we concentrate too much on concentration, if you would. So just a quick look at petroleum hydrocarbons and chlorinated hydrocarbons. And as mentioned before, petroleum hydrocarbons they're typically L-naples, but can also exist in neutral buoyancy and dense phase as well, whereas chlorinated hydrocarbons tend to be D-naples. You need to be careful about mixtures of these compounds. So co-dissolved plumes or mixtures of compounds where chlorinated compounds can exist within an L-naple and pose quite a different risk scenario. Petroleum hydrocarbons degrade aerobically and therefore biodegrade where there's sufficient oxygen, and we'll go through that in a little bit more detail, whereas chlorinated hydrocarbons degrade slowly under anaerobic conditions. And petroleum hydrocarbons degrade to water and carbon dioxide and methane under certain conditions, whereas, as mentioned, chlorinated hydrocarbons degrade to more toxic compounds, and TCE is 20 times more toxic by inhalation than PCE, and that's a particular prevalent risk drivers. And of course, TCE exists in its own right as a degreasing solvent where it can occur in quite huge concentrations. So the results of these are different behaviors in the subsurface. So if you look at the petroleum hydrocarbons, the plumes within water tend to have a plume front where they don't migrate any further due to biodegradation. And also similarly in the soil vapor phase, the biodegradation limits the extent of that soil vapor limit. And the opposite is true for chlorinated solvents, which migrate long distances in groundwater and can have quite extensive vapor phase plumes. And you can see quite clearly here that there's quite different risk scenarios to overlying properties. So biodegradation is key here, and be aware of mixtures of petroleum hydrocarbons and chlorinated hydrocarbons. And of note, there are other CSMs available. These are just very gross simplifications. So the reason for biodegradation of petroleum hydrocarbons and what that results in is kind of shown by this kind of classic graph here, where you've got on the y-axis you've got depth underground, and in the x-axis increasing concentration. So where you might have higher concentrations of petroleum hydrocarbons in the deep zone, so you have higher concentrations here, reducing significantly as they go up to up towards the ground surface. And the graph shape here is opposite to the concentrations of oxygen, which is entrained via the surface. So what is occurring here is biodegradation under suitable circumstances. And what's key here, what controls this is the flux. So it's the balance of the flux of hydrocarbons upwards and the flux of oxygen downwards. And typically the oxygen flux downwards creates quite rapid biodegradation, but it's important to know that these can be reversed as with chlorinated hydrocarbons. And reason for the reversal in flux here, if you're getting limited oxygen entrainment from the atmosphere, that can significantly limit biodegradation and increase petroleum hydrocarbon flux and VI potential. And there are a number of different ways in which that oxygen flux can be limited, either sealed ground surface, low conductivity soils, large building footprints. How aerobic is the ground near the center of those large footprints? Obviously, with big commercial buildings, they're quite often anaerobic near the center, and that needs to be kind of understood and taken into account. Perched groundwater bodies that are unimpacted can mitigate both the flux of oxygen and the flux of hydrocarbons upwards. LNAPL, that consumes oxygen, depends where it is in the soil profile, but if you're consuming oxygen, then you create anaerobic conditions, in a similar way that methane would if that was present in high concentrations as well. Anaerobic peak deposits, and also deep basements. So deep basements might be in the unsaturated or saturated zones where oxygen may not be that prevalent. So you kind of naturally have more anaerobic conditions in those locations. So just a kind of quick understanding. So I've kind of recycled this slide, which I think is useful just to again show the kind of the principles of diffusion and infection. So slow diffusion of VOC through water, through the capillary fringe, dependent on the moisture content in the soils, and also unsaturated zone diffusion, which tends to be slow, and really only rapid migration via infection as you get within a meter or less from the beneath buildings, and that's controlled by a pressure difference from the internal to the soil. But what's key here is so the key metric for vapor intrusion is the soil vapor concentration beneath a property. And so the key thing here is do we predict it from partition functions based on water and soil, or do we measure it directly? And hopefully by the end of this, you'll see the kind of real advantages of measuring it directly. And what we'll go on to talk about now are the uncertainties within the soil and groundwater sampling and vapor intrusion modeling, and these are really what are kind of discussed within the 1B paper. Again, I won't read through this, but really this is designed to give a workflow, so development conceptual model, and then assessment of your data against generic criteria. And then if your generic criteria, so if your risk assessment is relevant and sufficient, you would consider the limitations in sampling. Just going to move that. Limitations in sampling of both soil and groundwater. You might consider the parameter uncertainties and the limitations in modeling. And of course, modeling is also just as relevant to generation of generic assessment criteria as they are detailed criteria. So really, these are all considered as part of your CSM development. And where you identify potentially significant vapor intrusion risks, or whether the uncertainties and limitations are too great, the idea generally is that you would undertake soil vapor sampling, and there are a number of different publications, BSA 576 and SeRIA 682 VOC's handbook, although that's getting a bit old now, 2009. But in reality, you may wish to gather multiple lines of evidence at the same time, including soil vapor samples, if the CSM demands it, and particularly, as mentioned before, if there's a potential current acute or short-term vapor intrusion risk. Looking at the uncertainties in soil sampling, I've just picked out some of the key things here rather than go through the whole lot. I'm sure you've all read all three of those papers. So VOC heterogeneity and sampling, so it's very easy to miss the potential for VOC and significant source areas within a site investigation. And kind of ways around that, complete a robust phase 1 investigation prior to SI, and you might also want to kind of undertake PID screening of source samples and cores. Loss of VOC during sampling, and that's described a little bit more by Geraint. So it's very easy to lose the majority of VOCs, in particular chlorinated hydrocarbons, which have very high volatility, very, very easily lost during sampling of granular soils. PIDs don't differentiate between petroleum hydrocarbons and chlorinated hydrocarbons, so it's difficult to differentiate those in the field. And as Geraint will talk about, sample preservation may increase lab detection limits. And again, Geraint will talk about the ways to limit VOC loss using different sampling devices. And of course, soil vapor sampling, which would kind of limit the uncertainties associated with all of those. In particular, the loss of VOCs during soil sampling. Presence of NAPL, quite a big uncertainty, may be easy to miss in mixed soils, where you have sites with, for example, glacial till with sand and gravel lenses, with NAPL or high concentrations prevalently associated with those more permeable lenses. Very, very easy to miss through soil sampling. Also very easy to miss through soil vapor sampling as well. And chlorinated hydrocarbon odors and kind of visual observations are less obvious than, say, weathered petroleum hydrocarbons, which I think everyone will be quite familiar with. So it's really important design and the investigation and sampling strategies relevant to the geology. So that's really key. And soil vapor sampling can reduce the uncertainty in all of the above. In terms of groundwater, obviously monitoring well design, it's easy for design to miss or lead to misinterpretation of data for VI assessment. So key here is complete your monitoring well design based on your kind of robust understanding of your CSM and also based on site observations. So you need to understand what data is important and design boreholes to collect that data. You know, we see so many site investigations with single designed response zones, and quite often they really don't collect information that is useful. And importantly, are the wells designed to sample, identify and sample NAPL, which is obviously a key influence on vapor intrusion risk. So when we look at just three kind of typical scenarios, and really this is understanding how your sampling location can affect your interpretation of results that are relevant to looking at vapor intrusion risk. So the first one there, clearly the installation misses LNAPL and collects a sample from below, so that would tend to obviously underestimate vapor intrusion risk. As would the middle scenarios we're looking at. We've got floating NAPL, but at least we can measure that within the borehole. But if you take a sample from quite a bit below that, and you're just looking at the dissolve phase, which might have quite a significant concentration profile, then you could potentially underestimate vapor intrusion risk. And conversely, for D apples, if you were to sample D apples without really understanding what the significant concentration profile, and kind of understanding that again the key measure really is the concentrations of VOC within groundwater at the groundwater soil or capillary fringe interface, because it's from here that the VOC will diffuse into the overlying unsaturated zone soils. So again, really important to understand the kind of how your SI design, monitoring well design affects your sampling, or affects the results in your interpretation of potential vapor intrusion. Also important to measure the diffusion of VOC through water, including capillary fringe and wet or wet soils. So diffusion in air is about 1,000 to 10,000 times faster than in water. So the moisture content of soils and kind of understanding the kind of slow diffusion of VOCs through saturated zones, semi-saturated zones is really important. And obviously the depth of source has big implications here. A residual NAPL, so the residual NAPL has a similar risk profile to NAPL, but obviously by definition doesn't show up in wells. So how do you know it's there? You've got to be quite careful when you actually look at soil cores to identify whether it's residual NAPL. And chlorinated solvents can be quite difficult to see. So there are a number of visualization methods that you can use to look at NAPL in soils. And how representative is a PID monitoring of these wells? So we often see PID data from ground gas monitoring data. So how much TCE is 1 ppm? So the PIDs are typically the part per million PIDs rather than part per billion. 1 ppm TCE is 5,500 micrograms per meter cubed. And that's relative to the inhalation reference concentration for TC, which is 2 micrograms per meter cubed. And you can see what a crude device a PID is for quantitative measurement. And lastly here, low flow Persian sample. I'm not sure if anyone does use balers anymore, but they're certainly not suitable for VOC sampling. Looking at VOC concentration variability and heterogeneity. So it's quite easy to have partitioning to organic horizons and different strata permeability, different soil type and moisture content. And obviously the smear zone will give rise to quite a strong variability of VOC in the subsurface. There's poor correlation between chlorinated hydrocarbons between soil and the soil vapor phase, quite possibly due to loss of chlorinated solvents during soil sampling, transport, analysis, etc. Also partitioning is not as ideal as the partitioning functions would suggest. As we've seen, biodegradation, attenuation for petroleum hydrocarbons in particular. So soil VOC analysis don't take account of vapor phase biodegradation. Obviously, the sampling depth would have a big impact on this, depending on where they are in the aerobic or anaerobic zone. And mobility, soil VOC analysis don't take account of the potential mobility of the vapor phase, so you can get lateral migration of vapor phase through the unsaturated zone. So soil sampling in itself may kind of miss that, and there's also preferential entry routes laterally, which vapors can migrate through quite rapidly. And for groundwater, you can have quite significant VOC concentration profiles, and these will be very different for L-NAPL, D-NAPL, and neutral NAPL. So as mentioned previously, the key measure is the top of the water column and the capillary zone from where VOCs would diffuse upwards. So the location Principally, the depth of the water sample is critical for VI assessment, as we've seen previously. Changing groundwater levels, particularly important for LNAPL. So you can have, so you might think rising groundwater levels and rising LNAPL will reduce the source receptor separation distance and increase VI risk. It's also important to understand that when water levels drop, you increase the VI risk, not reduce the risk, or you can increase the risk because you open up a smear zone with reduced water content soils. You have increased diffusive flow of VOC upwards, which would tend to increase vapor intrusion risk. Again, depth is really important here in understanding how important that is. Again, we'll keep going back to biodegradation. It's so important for petroleum hydrocarbons. So groundwater VOC analysis don't take account of vapor phase biodegradation. And again, sampling depth has a big impact on this, whether it's so obviously the deeper the sample, the more conservative that would be. And so you can significantly overestimate VI risk from just looking at groundwater VOC samples. And just quickly here, I think I'm probably running a little bit out of time. So the partition equations to predict soil gas VOC concentrations assumes ideal theoretical partitioning at equilibrium. Now, these are lab calculated values, and they sometimes they don't have too much relevance to what's happening in the ground, so that can lead to quite significant overestimates of vapor intrusion risk. Again, the Henry's constant for TCE, for example, in groundwater can be 10 to 1,000 times greater than soil. The estimated concentration is 10 to 1,000 times greater than would be measured in situ. Predicted petroleum hydrocarbon soil vapor concentrations can be overestimated by several orders of magnitude if biodegradation is not taken into account. So again, quite conservative. So if you measure soil vapor and oxygen content concentrations directly, that will give you a much better idea as to whether biodegradation is likely to occur for petroleum hydrocarbons. And you may need to consider looking at a concentration profile in order to prove that that's actually happening. Again, going back to our old friend graph there, that kind of understanding that those relationships is quite key to understanding how prevalent biodegradation is. NAPL, obviously the CLEAR model doesn't take account of NAPL, where you have the potential for direct volatilization, so much higher risk potential. So in such circumstances, you should definitely measure the soil vapor phase directly. And where you have NAPL in fractured bedrock, neither are taken into account by in the CLEAR model. So definitely looking at the soil vapor phase directly is key there. Again, most models don't take account of biodegradation, so you would potentially overestimate quite significantly the vapor intrusion for petroleum hydrocarbons. So just looking at the key take-home message here then is that direct measurement of soil vapor VOC may significantly reduce the conservatism and increase the confidence in vapor intrusion risk assessment, particularly so for petroleum hydrocarbons. I just wanted to point out a few other kind of key things, really not necessarily directly related, but somewhat related to what we're talking about and things that we come across a little bit too often. So ground gas versus VOC risk, we quite often see sites classified by CS in accordance with BS 8485, quite often incorrectly so, with a statement that says with upgrade of a membrane for VOC. Whereas when you actually look into this, quite often the risks are actually driven by VOC, particularly for chlorinated solvents. So it quite often becomes not so much of a ground gas risk, but a vapor intrusion risk. And in which cases you would certainly need to undertake a detailed vapor intrusion risk assessment and mitigation design report. And they should be really undertaken by people with SoBRA Vapour accreditation. Again, there are a lot of people around who will offer to come up with a mitigation design, whereas they're not really don't really have the experience in order to do that appropriately, I don't think. Remediation criteria, see so often VOCs in groundwater. People will say that the VOCs don't pose a risk to control waters and don't consider the vapor intrusion risk from groundwater within remediation schemes. And this might be the last one, VOC membranes, it's really important. They do not stop VOCs, they only slow down the VOC flux. They can stop advective flux if they don't have holes in them, which can happen on a regular basis, but they don't stop diffusive flux. So all VOC membranes certainly should have published and certified VOC specific permeation rates and diffusion coefficients. And then with these, you can actually calculate the diffusive flux of VOC through that membrane and understand what additional requirements, for example, source removal or additional venting might be required as part of that remediation, part of that mitigation. And basements, consider VOC entry into basements, which could be in the vapor phase, dissolve phase, or NAPL. And then there are non-typical vapor intrusion routes for the entry of VOCs into those basements. And again, we don't really have time to talk about that at all. But as a last minute plug, I'll be going into that in a little bit more detail within the early careers talk in the middle of November. So I hope I haven't gone over time too much, but I'll let Geraint take the next stage.
Thanks, John. That was a very detailed, very interesting presentation. I might just shut off my video just to make sure I've got a stable connection so I don't drop out. But let me share my screen now. Hopefully everyone can see that.
Yeah, good. Thank you, Geraint. If you just go to full screen mode, that would be perfect.
Sure.
Great, thanks.
Excellent. Thank you very much for that. So this talk, and I guess the group focus really was much more on some of the practical implications, some of the considerations that we need to take into account when we're actually taking the samples. So it's probably less theoretical than the two other previous presentations that you meant, but more hands-on in terms of people who collect the samples. This is kind of guidance that maybe we need to be aware of if we're the people that are actually collecting the samples. So the presentation itself kind of follows the format of the report. So we're looking at things like sampling strategies. I know this was kind of covered in some of the previous talks as well, but it might be worth just looking in some of the details, some of the pros and cons of different kind of intrusive investigation techniques, different approaches to sampling. And that kind of feeds on as well to the different sampling methodologies. Again, looking at the advantages and disadvantages of active sampling approaches, things like canisters, etc. And then also passive sampling techniques, things like thermal desorption tubes with diffusive samplers. And I know it's not widely used in the UK at the moment, but on-site techniques like mobile GCMSs, for instance. And then we kind of, in the report itself, we looked at different analytical options. I think one of the key things is to consider the data quality objectives, what the lab data is actually being used for, make sure that we can achieve the lowest limits of detection, especially when we're looking at indoor air quality sampling. I'm going to touch very briefly on some of the lab suites themselves. So TO15, these are the kind of standard VOC suites that we're looking at, but also consideration of the permanent gases as well, part of the standard permanent gas suites that labs offer, the usefulness of having, as John mentioned quite recently, the usefulness of having the methane, carbon dioxide, oxygen concentrations sampled as well, with lab data alongside the VOC results. And also we're going to just touch on some of the drivers for robust data collection, the kind of quality assurance, quality control considerations we need to be aware of. So this is looking at kind of shut-in tests, helium shroud tests, awareness of the different types of tubing that should be used, all these kind of good practice, useful, practical considerations we need to take into account when we're actually collecting samples. But I also maybe got one or two kind of examples where things can go wrong and we can make the wrong decisions on site. And got an example where the wrong kind of helium grade has been used. And this was a very recent example, actually, but you can see when we go on to this particular part in the presentation, you can see what the implications of that might be. So it kind of touches on good practice, but we're also covering some examples of bad practice as well. So again, I know the previous speakers touched on this in quite a bit of detail, and maybe if I just cover it, I guess it's worth reiterating some of these kind of key points as well. But clearly from this slide, we can see the different approaches when we're looking at conceptual site models and what we need to do to decrease the uncertainty in decision-making processes. So I think conventionally, yes, we do take soil samples, we do take groundwater samples, and we make decisions on that basis. But if we are trying to reduce the uncertainty, and when we're looking at some of the complex sites, we do need to adopt a bit more of a multiple lines of evidence kind of an approach. As John mentioned, and I think David also mentioned, you do get high losses of volatiles when we collect soil samples. I think there's lots of published data in the US, and you could almost do another presentation on this particular topic. But I think there's something in the order of 80 to 90% of the VOCs are lost when we're taking soil samples. So we do need to consider other options, and that might be vapor sampling, or that might be use of preservatives like methanol preservation and in accordance with BS 10176. Yeah, I don't think it's hugely followed at the moment, but there might be kind of a requirement in the future to consider those kind of things. And when we're looking at groundwater monitoring, there is a high potential to lose VOCs if you are using kind of standard Baylor approaches, kind of traditional 3-well volume approach. And I would point you maybe to using things like low flow or passive sampling techniques. And I know hopefully people are using these kind of approaches a lot more, and also take into consideration the design and the construction of monitoring wells, making sure we're using kind of targeted short screen boreholes as well if we're doing groundwater monitoring where we've got particular interest in volatiles. And just have a better understanding about the design of the borehole in accordance with the conceptual site model, and obviously account for a kind of the groundwater level fluctuations that might be present. And for soil sampling, for soil vapor sampling, making sure that the monitoring wells are designed and constructed in accordance with BS 8576. I know that's been out for a little while, and I think that British standard will be updated in the near future, because it doesn't take into account the kind of very latest techniques for taking vapor samples, such as canisters. I know it was written some time ago, but I'm sure that will be updated. I think when BS 10175 is being updated, I think we'll see an update of 8576 alongside that, or maybe just a little bit later after that. So, typically boreholes might be shallow, narrow diameter boreholes to minimize any kind of ground disturbance. So these are kind of vapor sampling monitoring wells, which are outlined in BS 8576. And when we're looking at kind of near surface sampling from the outside of structures, those are kind of near slabs kind of samples. And then when we're looking at sub-slab samples, we're collecting samples from the actual building foundation or the slab itself. I think indoor air samples, those are not widely collected in the UK, and that's kind of a different position to the US, but it does allow direct comparison. Obviously, there's some disadvantages. That's very intrusive for householders. We do need to be aware of background concentration. So what we've seen when we've done indoor air sampling in the past, there's things like BTEX and MTBE. If there's vehicles where there's an attached garage, we've seen aromatic compounds where there's smoking and combustion that's taking place. There's, just trying to think of other examples, things like acetone from nail polish remover and other cosmetics. And you even see things like chloroform, which originates from things like disinfection, drinking water, bleach, etc. So these household items that can potentially impact indoor air quality. So we've really got to be aware of these kind of background concentrations. One of the other kind of big considerations, I would say certainly for indoor air quality, is the temporal variability. So with indoor air quality, you might get kind of worst case conditions in the winter time. rather than the summertime where you get kind of increased stack effects, lower ventilation. These might be considered as worst case kind of conditions for doing indoor air quality sampling. So lots really to consider, especially when we're doing indoor air quality sampling. Admittedly, there is lots of techniques out there for taking vapor samples, many different types of approaches. I think in our report, we focused quite a lot on canister sampling and the use of thermal desorption tubes for doing vapor sampling. And I think that the main reason for that is because they're the most common techniques. As I said, there are other techniques available. These are not the only techniques, but the focus of this presentation and the focus of the report that we published was on the more common kind of techniques. Each of these techniques has got their pros and cons, different advantages and disadvantages of these techniques. I would say from using both of these techniques personally, I think canisters, one of the key advantages for using canisters is you don't actually need a pump. There's nothing additional that you need. There's no kind of pump that's needed to when you're using the canisters. It comes under vacuum. By connecting the sample train or connecting a flow controller to the actual canister itself, that allows the sample to be taken. So I guess one of the other key advantages for that, there's less opportunity for operator error. So if you're using a pump, as you do with thermal desorption tubes, there could be a bit of uncertainty in how long the pump's pumped for, or the kind of the pump time itself. So there's a bit of uncertainty in terms of the operator error when we're using pumps. With canisters, we collect a whole air sample, and that allows laboratories to do multiple different types of analysis from one single sample. So that has also got some advantages. I think canisters are particularly useful for very volatile VOCs and some of the more reactive VOCs as well. Whereas I'd say thermal desorption tubes, they're well characterized for kind of mid-range hydrocarbons with kind of higher boiling points. And thermal desorption tubes, you need an indication of what contaminants are actually present, because that determines what kind of sorbent that you're looking for. So the types of sorbents that we use with thermal desorption tubes, Tenax, Carbopac, etc. You have to have an understanding of what contaminants you're looking for. You end up with many different types of sample trains and different types of packing that's used. And also you can get kind of breakthrough with the TD tubes as well. So especially if you've got high concentrations. One of the key advantages to the thermal desorption tubes, you can use them passively. So you have these diffusive head samples that you can place on the top of the thermal desorption tubes, and that allows you to extend that sampling period for a much longer period of time. And maybe it's worth saying at this point that these techniques, they're not mutually exclusive. You can use them together, and that's kind of this multiple lines of evidence approach that we're going to talk about further in the presentation. But yeah, using these techniques, you get fully quantitative data using the canisters. With the passive sampling techniques, we need to be aware that there's published uptake rates for things like BTEX, but not all the VOCs have got these published uptake rates. So if you're looking at doing passive sampling, that's one of the key considerations to be aware of. But having a fully quantitative short space snapshot in time using canisters, and then having kind of more of a time-weighted average concentration using thermal desorption tubes used passively, I can see some advantages in kind of both approaches being used together. And then, as I said, one of the other kind of approaches we can take, and this was a consideration when we were writing our report, was the use of mobile GCMS. And I think since the report was written, these kind of new techniques have moved on. And again, admittedly, they're not being used that widely in the UK, but you can get fully quantitative, high sensitivity, high selectivity kind of data. So it's not the disadvantages that John outlined with the PID, where you get a 10.6 EV lamp, where it's only going to ionize below that kind of lamp, and you're going to get almost like a total VOC concentration. We do get that selectivity, the sensitivity, the kind of detection limits are around what labs can actually achieve. You're getting real-time data, which also has many advantages. And we can look, by using this particular technique, we can measure concentrations at kind of vapor entry points, very useful for identifying preferential pathways, and also those kind of considerations we just talked about when we're looking at kind of background sources. And again, it's not either or. I would say that it can be used complementary with conventional methods, and we can use this particular technique to determine where we place our actual sampling, we can determine where we place the canister, where we place the thermal desorption tubes. Just to give an example of just some of the kind of different approaches that I mentioned. There's technique in the US that's widely used, well, or is used in the US, I would say. It's something called Vapour safe. There's another technique called frog, and these are all kind of mobile GCMSs. And there's another kind of approach called the SIFT MS, that's called selective ion flow tube mass spectrometry. So there are these approaches available. Some aren't available in the UK. I don't think they're quite widely used at this moment in time, though. When you have discussions with the lab, or when we're considering how we're collecting the samples, I guess one of the key discussions we need to have with the laboratory is what type of samples we're taking. Are we taking indoor air samples, which is on the left-hand side? This is called a flow controller, or a CS1200E flow controller. That would be used for taking outdoor air samples or indoor air samples. Slightly different sample setup, and the sampling itself takes a lot longer. Or if we're doing soil vapor sampling, where we're connecting a sample train to a canister, and that would normally be done in a short space of time, and involve a slightly different kind of sampling setup using a sample train. But in both cases, actually, what we have to do is to check the vacuum that's in the canister, and there's a separate gauge that we use just to connect to the canister, and that's just to check that the canister is under vacuum. If it's not under vacuum, we don't use the canister. But and it should be around 25 inches of mercury. So you can see on these kind of gauges that we use, it should be around that kind of level. For soil vapor sampling, we normally take a sample at about 200 mils a minute. So it takes about 10 minutes to take the sample, depending on the size of canister that you're using. And I said different flow controllers for doing indoor air sampling. They can be set up to take samples over 2 hours, 5 hours, 8 hours, or 24 hours. So there's different options depending on what the requirements are. And it's a discussion to have with the lab. But typically what we would do would be to stop sampling when the gauge reaches between 3 and 5 inches of mercury, then make a note of exactly where you stopped it. And that's back calculated by the lab to determine what the actual concentrations are. I wouldn't let the gauge go down to 0. That's not what you meant to. You meant to have some vacuum still in the canister. And it's also good practice just to provide the laboratory with any PID measurements, so they know if there's particularly high concentration samples. And there are, as I mentioned, different types and different sizes of canister. On the left-hand side, that's just a 1.4 litre canister. That's pretty much used for most applications. And then there's a smaller canister, which is a 450 ml canister in the middle. And there's something else, which is a bottle vac, which is slightly different to the other approaches, but can be used for the similar applications. But if you know you've got particularly high concentration samples, the lab are actually reusing the canisters. So they clean the canisters, go through this very long and robust kind of cleaning cycle. But if we know that there's high concentration samples, I would recommend using the bottle vac, because that's almost a disposable device, whereas the other two do go through this kind of cleaning cycle. And I think with the 1.4 litre canisters, I said, you can pretty much use the 1.4 litre canisters for most applications. If you were just interested in looking at TO15 and looking at kind of a VOC suite, then that's fine. You could use the 450 ml canister, but it would depend on the duration, how long you were sampling for. So there are different options. The bottle vac would be used for high concentration samples, but just to be aware, there are these kind of different options that are available. I think John mentioned the advantages of also being able to determine methane and carbon dioxide, etc. There are different suites of analysis when we're looking at laboratory, different techniques. There are key parameters that we can look for. We can look for things like C1, C7, that's the ethene, propane, butane, etc. The TO15 suite, what you typically see when you get results back, the results are reported as micrograms per meter cubed and ppm. But the labs analyze kind of a list of, it depends from lab to lab, but They analysed a list of around 70 individual VOCs. And like soils, unlike water samples, we can ask the labs to report any tentatively identified compounds. So within a certain level of certainty, the lab can provide data on these kind of tentatively identified compounds. So they might not necessarily have standards for them, but they can say with a certain level of certainty that these compounds might be present in the vapor samples that we've submitted to them. And also, quite usefully as well, labs can analyse the TPH and almost give you kind of a criteria working group approach, where we get the aliphatics and the aromatics, obviously key for some of the kind of petroleum hydrocarbons that you might be looking at, some of those kind of sites where we need to look at the TPH concentrations as well as the individual VOC concentrations. There was a big focus on QA QC in the SoBRA reports that we published, and we do need to be aware of these kind of different techniques that are available. I guess one of the common approaches we can take is a shut-in test, and you might be aware of how this kind of principle works, but what it does, it kind of creates a closed system between the canister, the gauge, and the flow regulator, where any loose connections in the sampling system can easily be identified prior to sample collection. So it's a nice, straightforward, easy way of determining if there's any kind of loose connections. And if there is, what you're meant to do is kind of tighten up those connections and go through that kind of shut-in procedure again, just to make sure that there's no kind of loose connections. And I would say probably not that widely used, although I've been involved in probably, I would say, a handful of projects where a helium shroud test has been used. And this is to determine the kind of integrity of a monitoring well, to check for any atmospheric leakage. What we do here, we introduce helium for several seconds. And to be fair, that's probably usually enough to create kind of conditions in the shroud where we can read up to about 10% helium. And this can be measured in the field with a helium analyzer. And there are companies that can hire helium analyzers. I would recommend a particular type of helium analyzer. It's called an MGD 2002 helium analyzer. I think that's also referenced in a lot of the US EPA guidance that you see out there. But it's probably the most appropriate approach to take if you're analysing helium in the field. A small amount of the tracer in the actual sample itself doesn't actually indicate that it's an unreliable sample. But if you look at some of the guidance, and this was referenced in the SoBRA report as well, if you look at some of the US EPA guidance, I think most of the guidance allows up to about 10% of the starting concentration before the sample's considered compromised. There are many other kind of quality control type samples we can take. We can take duplicate samples, where the lab can provide a kind of an extended sample train that allows you to take two samples at the same time. Also, we can use things like trip blanks, as we would do for kind of groundwater sampling. But for trip blanks, when we're looking at canisters can be pressurized with things like nitrogen, and they can be shipped out and sent back to the lab. And then if you're doing things, if you're using like vapor pins, for example, a nice, easy, practical way is to kind of have this water dam set up where you're doing kind of sub-slab sampling. And that's a really straightforward way to determine if there's any kind of leakage. But if we look at 85760 and the kind of guidance that provides to us in terms of the frequency of sampling, I think in terms of QC sampling, I think it recommends about 1 in 20 samples should be QC samples. And again, you know, this is kind of straightforward, practical, good advice, but always use kind of dedicated sample tray materials. The labs should provide these kind of materials. Be careful about the selection of tubing. Obviously, the tubing itself can lead to off-gassing of VOCs. So labs typically will provide things like Teflon tubing, but there's certain types of other tubing that we would not recommend. So just to be aware of that. And don't reuse tubing. I've seen this being done in the field as well. Normally, the labs will provide many meters of tubing, and if you ask them to provide more, then that's fine. They'll be able to provide more. So it's something that you shouldn't need to reuse tubing. It should be dedicated to the borehole, and then move on to the next one and set up a separate kind of sample tubing, and then attach that to the monitoring well. And try not to have the sample train open when we're not taking the sample as well, just to avoid any kind of obvious cross-contamination. Now, the report considers the pros and cons of different leak detection techniques. one of the key things I would mention is don't use party grade helium. It's very cheap to buy, and there's reasons why it's very cheap to buy. There's lots of VOCs that are present, and the next slide kind of covers that in a bit more detail. But only use lab grade helium. I would maybe just kind of word of caution about liquid traces, because you can't measure the concentrations in the field, so you can't relate that back to the lab analysis when you have that reported back. And also liquid traces are often applied at really high concentrations. So you're more likely to end up with dilutions back at the lab. Things like isopropyl alcohol, IPA, limonene, etc. They can lead to false positive results when the lab are analysing for TPH and volatiles. And I doubt if it's that widely used, but the sulfur hydroxyfluoride, that is a potent greenhouse gas as well. So I think there's kind of been a move away from using that as a leak detector tracer gas. This was a very recent sample that we analysed, and it was party grade helium. And you can see here where we've got high concentration. So this is a very cautionary note to use only lab grade helium. And some of the labs can provide the helium to you, but please don't use party grade helium, because obviously you can see there's some particularly high concentrations of VOCs that we're actually looking for when we're doing the vapor sampling. So yes, a word of caution there. Don't use the kind of cheap party grade helium that you'd be able to get from supermarkets, etc. This slide kind of covers the standard VOCs that are typically analysed by the labs. I would say that every lab has a slightly different target list, and the original TO15 target list come from the US EPA's kind of Clean Air Act. I think that references about 97 different hazardous air pollutants. And yeah, they've got different boiling points, different vapor pressures, which means they can't actually be analysed by canisters. So, for example, phosgene, that's one of the kind of listed TO15 compounds. So some of them can't be analysed by canisters. So I just be cautious when you see the reference of TO15, and that's been updated quite recently to TO15A as well. So there's certain things on that list which will not be able to be determined by labs, but it's an extended list, and each UK lab may say that they've kind of referenced TO15, but it's not a full TO15 list, and each of the UK labs will have slightly different suites. So good to be aware that there might be some inconsistencies between each of the different labs, and because it's based on TO15, you do see things like methylene chloride reference instead of things like dichloromethane. So some of the terminology might be slightly different to the way that we see some of the VOCs reported. And just thinking again about the kind of lab analysis, you see some of the labs kind of offering batch certification, which is where canisters, as I mentioned, they are reused. So it goes through this kind of cleaning cycle, which involves heating, purging with nitrogen, and then it follows kind of cycles of filling and evacuating. So with batch certification, the canister with the highest concentration is reanalyzed. So there might be a batch of, say, 20 samples. The sample with the highest concentration is reanalyzed to make sure that there's no cross-contamination, but it's only the one sample with the highest concentration. So that's called batch certification. I think most of the labs analyze individual certification. So that means where they reanalyze every single sample, regardless of whether it's the highest or the lowest concentration. So there's a difference between batch and individual certification, but it's worth highlighting the fact that there is this difference. So once the sample is ready to be sent out, what the labs do, they leak check every single can, and then they kind of make sure before it's shipped out that there's no leakage. But that's the reason why when we're in the field, we're also checking how much vacuum's in the canister, and that's why we use kind of a separate gauge to make sure that there isn't any leakage from the canister. But this is all part of the kind of QA/QC that we're following, and it is kind of referenced quite a lot in our guidance. And I'll just briefly mention about the lab analysis, because it's kind of part of our data quality objectives as well. When labs receive our samples, They'll normally take a small volume of sample, typically like 5 mils. Each lab might have a slightly different approach, but the labs will take 5 mils of sample, and that's just to get an idea of the concentration, because if they had a particularly elevated sample where there's high levels of TCE, for example, that could cause some instrumentation issues. So they follow that up when they know that there's no requirement to do very high dilutions, or if there's no sky high levels of TCE, for example, they'll then take 100 mils of sample. So just to give you an idea of how the lab analysis is carried out, on the right of the picture, we're seeing some carbon dioxide cylinders, and that's what the labs use for cryogenic cooling. And then just to the left of the cylinders on this picture, there's an auto-sampler containing the gas samples in the canister. That's the kind of standards that we're using. And then also in the large 6-litre canister, that contains the actual internal standards that the labs reference. And then the top of that, where the GC system is, that cryogenically traps a sample and concentrates it. And the gas is put on kind of a trap and heated up, and that produces kind of almost like a tight plug of analytes. And from that point onwards, it's just traditional gas chromatography analysis, or GCMS analysis. Labs can use a SIM method, selective ion monitoring mode, where they're looking specifically for individual VOCs. Instead of looking for that targeted list of 60, 70 compounds, they're using SIM, which more accurately allows them to determine things like benzene or TCE or PC or vinyl chloride, etc. And by looking more specifically for those compounds rather than doing a broader targeted list methodology, we can achieve lower detection limits using that kind of an approach. So just thinking about what we've covered there, again, just reiterating some of the good points that come out of the previous presentations. Obviously, robust, reliable conceptual site model, that's obviously key. I would say collect credible data, discuss data confidence. We're trying to reduce any of the uncertainty to acceptable level to make any decisions. I think that's the key point. More complex sites will definitely require multiple lines of evidence. We need to be aware that spatial variability may be high for soil vapor sampling. I would say be higher for soil vapor sampling would be for indoor air. For indoor air, I think temporal variability would be a bigger consideration to think about. There are reliable methods that exist. Certainly for vapor sampling, we've seen some of the different techniques, how active samples compared to passive samples, how high resolution real-time samples have other kind of advantages as well. But have a discussion with your lab, make sure that they're aware of what your requirements are. Definitely consider QA/QC when we're taking our samples. Think about the shut-in test that we've mentioned, helium shroud, potentially taking duplicate samples. Be aware that different limited detections are available as well. I have included some references. Some of these update the original references in the SoBRA report, but it's worth looking back at the original references as well. I have detailed the SoBRA documents, but I know there's links that you'd probably be fully aware of anyway. But with that, I will ask if I will pass back to Etni to see if there's any questions.
Amazing. Thank you so much, Geraint. Yeah, please to all our attendees, please do put your questions for him in the Q&A function. And a massive thank you to all of our speakers, Mel, David, John and Geraint. That was a really comprehensive overview of vapor intrusion risk assessment and really, really useful. So thank you so much for that. I'm going to kick straight off into questions so we can get started. I'm going to start with the first one, which I know a few other attendees kind of commented on as well, but just to throw it back to you, David, because this one came in when you were presenting. One of the attendees has said, call me cynical, but can't you just install an appropriate vapor protection membrane in a floor slab to mitigate risk from VI rather than spending the time and expense of doing complex modeling, which is inherently fraught with uncertainties?
Thanks, Ethne. I think I did see the little conversation go through on the Q&A there and on the chat. I think so. One point was pushback, which is very valid, is that if you're building a new building, it's a possibility. There are still caveats, but obviously, if you're looking at existing buildings, retrofitting can be complicated, difficult. If they're off-site receptors, as was mentioned on the chat, then just getting access to off-site properties can be very difficult, impossible even. So there's that side of it. if you go back to if you are putting a nice new building on a site, and I did see the response, you know, is it an appropriate vapor membrane? I think if it's a highly contaminated site with high vapor concentrations, you have to demonstrate that appropriateness, as John's presentation showed. That vapor membranes don't prevent entirely migration into the building by diffusion. So you have to look at the diffusion characteristics of a membrane and be happy that it's going to do the job. And I think you can always say, well, it's appropriately installed. It's still difficult to validate that and guarantee it, especially for the long term and the lifetime of a building. So I think that would be my answer, that it's part of a solution, but especially on highly contaminated sites, I don't really like to see it just put in as a this will solve the problem.
That's really. Oh, sorry, John. Did you want to comment on that?
Yeah. If I could just add to that, I guess one of the issues of just putting a membrane is it could lead people to not characterize the conditions of the ground beneath the buildings. I mean, we're not just talking about vapor intrusion risk, we're talking about risk to controlled waters. There are other exposure risks. Of VOCs, you would have direct contact exposures, dust inhalation exposure risk. It's not just vapor intrusion. And there's also, you know, a sustainability issue with regards to fitting membranes when they're not required, and that's relevant to ground gas and VOC. And the last thing really is, it's not just as simple as putting in a membrane. So a membrane has to be put in properly, and there are implications to the build out of properties for putting membranes in. They have to be, if you're going to put a membrane in, they have to be verified properly. And there are also kind of implications for follow-on trades in terms of protecting that membrane. So there's no point putting in a membrane in if follow-on trades are going to come and puncture holes, which is really common. So, you know, as for a radon membrane, if you have a single a hole in a radon membrane, it pretty much makes it ineffective. So you get that vector flow through holes in membranes as you do through gaps in concrete floors, etc.
That's really useful. Thanks, John and David, for that. I've got a question for you now, John, actually, which came in during your presentation, which is, if the only likely source was a volatile one, for example, petroleum hydrocarbons, do you think any UK regulators would forego soil data if soil vapor data was available?
Again, I think it's what you want to do is inform your conceptual model. So there are uncertainties in collecting groundwater data, there are uncertainties in collecting soil data, and also uncertainties in collecting soil vapor data. So I think it's more sort of collecting information from all those different compartments. You know, this so-called multiple lines of evidence approach, where you collect data from multiple compartments and you look at all of that and see where that points in terms of risk. I think there's always a little bit of a risk with saying, well, we'll do without soil or groundwater sampling and just concentrate on soil vapor. Again, it's kind of really understanding the kind of conceptual model and those kind of multiple lines of evidence.
Great, thank you. And Geraint, there's just been a comment put in the chat that says, given that the purpose of the vapor intrusion investigation is to protect human health by assessing exposure risks, surely indoor air monitoring is the most important of all the measurements discussed. I wonder if you had any comments on that, and also just in relation to that, do you think that land contamination specialists should be working more closely with indoor air quality professionals on topics such as this?
I'll answer the second part of that question first, then. Yes is the answer for that. Yeah, that would be useful. I think it's kind of one of these, the more people with different disciplines are involved in it, I think that would be useful. In terms of taking indoor air samples, the kind of approach that the US take, because there's more risk from litigation in the US, is they go straight to doing indoor air sampling, but there are uncertainties with that. I know there's kind of these background concentration issues that we mentioned, and also the disruption to the kind of household as well, the residents. So there are some uncertainties in taking indoor air samples, and it's more kind of a multiple lines of evidence approach that we take in the UK, where we're looking at different investigation techniques. But I'm sure John and David could also have comment on this particular subject.
Thank you. Yes, John or David, would either of you like to come in on that point?
Yeah, I think certainly when it seems like an obvious thing, isn't it? If you've got VOC under the ground that are getting into buildings, why don't you just measure in the building? I mean, as Geraint pointed out, I mean, there are quite significant implications of actually going into someone's house, particularly if it's under the kind of the planning regime. I mean, there's kind of instant blight. So I've been involved with a number of projects where, and you're actually measuring in people's houses, and there's quite a big impact on the people in those houses and on the value of their properties until you can prove that they're safe. But the other thing as well, it's not as simple as just going in and collecting an indoor air sample. You've really got to make sure that indoor air sample is first of all representative of kind of exposure over time. And as Geraint pointed out, the temporal variability in indoor air quality is quite significant, and the kind of the spot sampling methods can very, very easily miss patterns in data which lead you to kind of understanding why concentrations are elevated in the first place. And so indoor air sampling needs to be undertaken very, very carefully.
That's useful. Oh, sorry.
Yeah. No, that's fine. I think that's probably about it.
Amazing. Thank you, John. David, are you happy that's been covered, or did you want to add anything?
Yeah, no, I think the temporal thing is important. If there's some quite in the OSWA guidance, some quite interesting studies you see where, you know, over the seasonal changes, changes. So it's got to be really carefully planned and implemented, and over quite a long time frame to capture those kind of full annual seasonal changes potentially. And like John said, that's quite an intrusion, especially if it's private properties.
What I was going to add is that the quite often what we're looking at in the ground is ubiquitous within the properties in terms of background concentrations, and it is not as simple as kind of assuming that you will get a definitive answer from looking at indoor air quality. Quite often it opens up another can of worms that you have to try and answer.
Great, thank you. And another question for you, I think, David, it came in when you were talking, which is how significant are floor cracks in modern construction techniques, and how do we accurately quantify these in our modelling?
I don't know how well qualified I am to. I mean, my gut feeling on that would be that modern techniques are probably better at reducing cracks, but how that develops with time is still probably pretty uncertain. And I mean, I don't know how you would, I don't think you could give much certainty on that. So you would have to assume that there's likely to be some floor cracks in even reasonably well constructed and engineered buildings. In terms of how well quantified they are in modeling, not what it's an assumption, it's an estimate, and people tend to leave it the same, when they're doing things. And so I would say it's not particularly well dealt with on a site-specific basis, because you just don't have the information.
Okay,
Yes.
Thank you, David. Yep, John, please.
If I can just add into that, so the floor cracks within the clear model are actually contraction cracks around the perimeter of the floor slab. So when the concrete cures and contracts, it can leave a small opening around the perimeter of that crack. And also we come across it a lot with kind of slab pouring within deep basements, and where we have kind of waterproofing requirements. Then there are particular techniques that you can use to limit crack openings to 0.2 or 0.3 millimeters, and so they're quite well defined. And again, in those types of scenarios particularly where you've got water ingress, which can also carry in VOCs in the dissolve phase, or potentially free phase, and potentially gaseous phase, those cracks are fairly, they're observed by water coming in, and there's depending on the grade, on the kind of moisture grade requirements of that environment, that there's a requirement to fix those cracks quite often through sort of pressure grouting. But I would also say that there are a number of other types of construction joints. So there's something called an armored construction joint, which is quite often left open to allow for expansion contraction in the joint. And we've seen circumstances where those armored joints have been left open, and with gases and VOCs coming through that armored joint. And further exacerbated because during the construction of the armored joints, the membrane, if it's put in, is quite often punctured through rebar that's used to support the armored joint, and they're quite often not repaired once the rebar kind of stabilization for construction of the concrete slab is taken out. The membrane's not fixed, and so they've got quite double areas for ingress of VOCs. But I guess that's quite specialist to those construction types of joint in larger buildings.
Great, thank you, John. And then just time for one last question, which is the last one in here actually, which is great. We've got through them all. Is the use of screening distances seems well established in the USA. Why do you think that we're behind on this aspect in the UK? And this came on during your presentation, John.
I think there are a number of differences, and I think it's quite important to highlight these. So firstly, screening distances were developed by US practitioners, and primarily for small UST sites, the small underground storage tank sites such as petrol stations. And whilst so there's quite a clear science of kind of, you know, if petroleum hydrocarbons biodegrade fairly rapidly, then the science effectively says that there's a limit to how far these things will migrate, either in the groundwater phase or in the soil vapor phase, because of this biodegradation. And so what the distance screening criteria approach sought were these kind of conditions under which soil vapor intrusion is unlikely to occur. And I think whilst, you know, I think whilst the science is sound, I think applying those as rules does come with problems. And I kind of wrote down some of these before we started. So one of the things is that in the UK, so if you're looking at a UST site and you're trying to predict what a screening distance, an exclusion distance would be for an off-site property, for example, that might require you to investigate off-site in order to show that a solvent plume or a petroleum hydrocarbon plume hasn't migrated significantly off-site. And in the UK, certainly from my experience, and I'm sure experience of most practitioners, is we don't do a lot of off-site investigation. You know, on our site, miraculously, contamination stops at the boundary. You know, it's just, maybe that's just specific to the UK, but our contamination doesn't leave our site boundaries. So that's one thing. So you would have to really understand and potentially undertake more off-site investigation. And there's also a need to better understand, so the data requirements to support those decisions are also more. So within the kind of US guidance, so you might need more site investigation data to better characterize source location, plume extents, etc. And you might need to provide proof of non-expanding plume fronts. So if your plume is still expanding, then it's very difficult to really say how far that's going to extend off-site. So again, you would need to undertake more investigation, and if you're kind of restricted by your site boundaries, you may not be able to actually obtain that information. Because quite often, you know, you drive onto a petrol station site, quite often the tanks aren't right in the middle of the site. They're often on the boundaries, and often on the down hydraulic site boundary, just by chance. And also, you'd also need to understand off-site conditions, so the source, the geology, the receptor. So I think whilst kind of rules can be useful, I think their kind of application needs to be undertaken quite carefully, because if you had a rule, then you will get people who go to site, they'll undertake minimal investigation, use these rules and go, well, hey, well, we don't have a problem, without really kind of appreciating that they haven't collected enough data to really justify the use of those rules. That would be my point. The science is good, but it's just how you apply it needs to be done very, very carefully, I think.
Thank you, John. That's a really useful answer. Makes a lot of sense that, yeah, the difference between how you apply it is so important. So I'm afraid that's all we have time for today. I want to say a massive thank you to our speakers, John, David, Geraint and Mel. It's been really great to have you here today. So thank you for taking your time out and presenting. And thank you to all of our attendees as well for coming along. I hope you found that as useful as I did. And if you're an IES member, don't forget to record your attendance using the IES CPD tool, which you can do by logging into the members area. Just to let everyone know that the webinar has been recorded and will be made available on the IES website and YouTube channel. And just to flag a couple of the next IES events. So on the 25th of October, we have an online training event on shaping systems and learning how to engage with environmental policy. And our next webinar, a couple of days after that, is on utilising remote sensing and machine learning artificial intelligence to support more effective land management. And both of those can be booked on the IES website. Another massive thank you to the speakers and to all of you. Have a great rest of your day. Thank you.
Okay, thank you.
Thanks, Stephanie.